Yep.
Right, shall we start? So, my name is Gregory, I'm the Director of Investors in Doctoral College, and this is one of our annual events where we hold Doctoral and Inaugural Lectures for the three separate colleges. So we've had one for Life Sciences, one for Arts and Humanities, and this is the first one for Science and Engineering. It's a real pleasure to have the opportunity to come and introduce two really fantastic lectures from students who have been selected competitively against their peers. So to get to this point, actually just to be in the running is a fairly major achievement, and then to be selected to give these lectures is really great stuff. And we're really looking forward to hearing what the two of them have to say. This is kind of the best of the best for science and engineering in the PGR sphere. So I'm just building you up now, just so we can have a bit of fun. So our first inaugural lecturer is Greg Hunt. Greg is now, as you can see, at Imperial College London, which is an inferior institution to Leicester, obviously, but we have to get that in. And Greg's going to talk to us about Saturn's auroral current systems as revealed by the Cassini mission. So we look forward to hearing what you have to say, Greg. So
Alright, thanks for the introduction, and also a big thanks for selecting me to give the lecture as well. So yeah, I'm going to talk about the auroral current systems. So the aurora is the illumination that we see on this image, which is a Hubble image with then a Hubble image of the aurora superimposed on it. And these are fed by large-scale electrical current systems that really connect the upper atmosphere of a planet to its space environment. And the currents I'm going to be talking about actually flow along the magnetic field lines, and you can think of it kind of as a wire diagram. But we're going to first introduce a bit about Saturn and some of its background and history, some of the previous observations, and there's going to be sort of a tour of work that's also been done at Leicester before my PhD, and then my PhD work, and then a little bit about what we're doing at the moment. The Cassini mission ended last year, which was around the time when I switched to move to Imperial, which is where I'm now. So these are the first sort of measurements that were made of Saturn's magnetic field, just to give you the sort of some of the history of it. So we had three flybys, all in between the late 70s and early 80s, with the Pioneer 11, the Voyager 1 and 2 spacecrafts. And these sort of flew past Saturn just in one pass, and really opened up a lot of questions about Saturn and sort of led the groundwork for Cassini to be proposed to go back to Saturn as an orbiter. So the first measurements really showed that you had so this is the time along this axis, and then this is the strength, the total strength of the magnetic field, and we had a field that was around 20,000 nanotesla at the equator, which is about 10,000 nanotesla smaller than the Earth's at the equator. And it also revealed something really interesting about Saturn's magnetic field. Although it appeared to be a dipole, like a bar magnet, it was also incredibly aligned with its spin axis. So at the Earth we have a tilt between the spin axis of the planet and the magnetic axis. So like at the moment, like the north pole of the Earth is somewhere in the Canada's Arctic region. At Saturn though, from Voyager measurements, though, it was determined to be about less than 1 degree tilt. So the Earth is about 11 and Jupiter's the same or similar. And so this is still an ongoing puzzle and mystery at Saturn as why it's so axially aligned or axially symmetric. And so this magnetic field or large magnetic field that Saturn has then creates a region of space or a region in space around the planet where the magnetic field dominates over the magnetic field that comes from the Sun. So this schematic here shows the region of space called a magnetosphere, which is this bubble, a magnetic bubble in that space environment that comes from the Sun. So way off over here, we have the Sun, which is giving out plasma, which is a charged state of a gas, which then carries out the solar magnetic field out into that interplanetary space. So the space in between the planets is filled with this plasma and magnetic field. Now when it comes across a planet which has a magnetic field, like Earth, but in Saturn as well, we then have a region where the magnetic field of the planet carves out that space. And so at the front we have what's known as the bow shock. So this is where the solar wind is coming at you at supersonic speed, and then hits an obstacle and you have a big bow shock, or like a shock wave that sits upstream in that flow. And then you have several other boundaries which then denote where you have sort of pressure boundaries between the internal systems, so the Saturn's magnetic field and plasma, but also the stuff coming from the solar wind, and you have this balance of those regions. So in Saturn's system, we have deep inside Saturn, this isn't to scale, but at around 4 Saturn radii out, we have a little moon called Enceladus, which it was discovered had plumes of water vapour, which then outgas from cracks in the surface, and this actually then fills the magnetosphere on the equatorial plane, which is this sort of slice here. It fills a big plasma disk, which then affects the magnetic field. So the magnetic field starts to sense those charged particles, which are the plasma, and that starts to then add weight or mass to the field lines, which then can bend them. And actually, we'll talk a little bit about that in terms of how that affects then the magnetic field and drives some of these currents where you have what's called subcorotation or plasma, which I'll talk a little bit about later. In the region up here, which is where like most of my research has been taking place, is where we have the auroral field line currents, or what we just, which give you then the aurora, which sits on the planet here, and accompanying those really intense currents are radio emissions. We'll talk a little bit about the radio emissions because they add to a bit of a story about how long a day on Saturn is, or how long a Saturn day is, which is still a mystery. And so we'll talk a little bit about that and how the currents that I've studied link to them. So I thought I'd just show some pretty pictures. These are actually a set of Hubble Space Telescope observations by Johnny Nichols, that's also at the University of Leicester. And these were taken, I think, in 2014 or 2013. The paper's published in 2014, which show really dynamic, intense storm on this side. So this is, you're looking down on top of the northern pole of Saturn. So the sun is off to the bottom here. So this is noon, and this is the dawn side. So 6 o'clock local time, and this is dusk. And you can see that over the course of, so this jumps about 10 days or 15 days, I think, something like that. Yeah, 15 days. And you can see in this period we have a really dynamic storm, which then fades away, and you can see that it disappears. And all of this is being driven by dynamics in that magnetosphere, the plasma interaction, and also being coupled with those strong electrical currents, which we'll talk about in a minute. So to really understand what's going on here, you need to send a spacecraft there, as well as using auroral observations like this. When you send a spacecraft there, you can then actually sample the space above these regions. So we fly through those field line currents, we fly through all of the plasma which is connected to the auroral and the northern and southern lights of Saturn. So to get there takes a long time. So this is Cassini's interplanetary journey, and also there are some sort of my life milestones marked on here as well. So the launch of Cassini was in 1997. I was 7 years old, and I was just started primary school. Cassini then went into the inner solar system to pick up some speed by doing some gravity assists around Venus. Again, this was all while I was at primary school, starting to get interested by space, and still playing with Lego, which I still do today, so not really grown up much. And then there was an Earth flyby in 1999, and then out to Jupiter when I was age 10, and Cassini arrived when I was 13 and making choices about GCSEs and stuff, and I watched a really cool Horizon all about Cassini arriving, and I was like, that's really cool, and carried on studying science. And then Cassini spent from then through to 2017, September 15, where then the spacecraft spectacularly entered the planet by doing a series of orbits in between the planet and the rings, and then eventually entering the upper atmosphere, or the atmosphere of Saturn, around noon in the UK. I was age 27, a postdoc at Imperial, and I was half asleep at the Caltech event, which was 5 o'clock in the morning in LA when they crashed the spacecraft. So these are some of the early observations from Cassini, which was work done by Leicester, including one of my supervisors, Emma Bunce and Stan Cowley. And these were looking for the first time at these Hubble observations with then in situ measurements. So this is showing you that plasma. These are actually electrons, and where you have the bright colours is where you have some warm electrons, and here we don't have any electrons at all. And this is the magnetic field component that we see large changes in the magnetic field when you fly through these currents. So if you think back to school and you have a wire and you pass a current through a wire and you move a magnet, or you move a compass around that wire, you see a change in the magnetic field. You have a magnetic field around it. That's exactly what is happening here. Same physics. And so in this is the phi, so this is the azimuthal, so it's the component that's like in that direction around the planet. We see these sharp changes, which is also the component that you would expect to see a tilt in the axis. And because we don't have a tilt, then we can really pick these out very clearly just by looking at this component. So this was published in 2008, and also in 2008 Cassini went on to do lots more high latitude observations flying through this region, which is what then the data set that I analysed for my PhD was. And I should just point out, in 2008 I was starting my undergraduate degree, so the steps towards this point are filling in. And then that study showed that there was actually two types of signatures. So here we had one where you just in the north had a negative deflection in this azimuthal B phi, and in the south you had a positive deflection, which indicated that the field was always lagging. So the field lines, and I'll show you in a minute exactly what that means, but imagine if you've got a garden sprinkler or something like that and you bend, if I had a piece of rope and started winging it around my head, you'd see it bending back from the way I'm turning it. There was a second signature though where we actually saw where you saw that the field goes negative, but then it also goes positive and overshoots, and likewise in the opposite sense in the other hemisphere. So it's there was two types. There was called type 1 and a type 2, with the predominant things. So that leads me on to the first sort of electrical current system that we're going to consider, which is this one. So this is associated with this structure in the magnetic field. So this is what I was talking about. If you're looking down on top of the planet, this is a magnetic field line and it's bending backwards. So the planet's rotating in this direction, but the magnetic field line is bending back in the other direction. And you can have a case when you have a leading field, which is when this actually bends the other way. So you start to bend forward in the rotation. And so this is a schematic of kind of the current system that would give you the magnetic field perturbation that we see. So again, through that idea of you pass a current along and you get a magnetic field deflection. And so we have these are the azimuthal fields here, and the currents are shown in green, and the black are the field lines. And this is a view just looking down on top of the pole, and it shows a ring of current. So you have a ring of upward current. So where these are coming out the board, that's where we've got current flowing up towards us, and that's where we have the aurora. So this was the one that was really considered in early works and modelling work that was done even prior to Cassini. And those observations I just showed you sort of supported that, but it doesn't quite explain why we have these two types of signatures. Which then leads me on to this other question part. So I'm saying this is what's called subcorotations. You're rotating slower than what Saturn is rotating at. So that asks the question, how long is a day on Saturn? And it's about 10.5 days, but we don't actually know the precise answer. So obviously on a gas giant you can't just pick out a piece of land and follow that round for rotation. And then at Saturn it makes it tricky because we've got this axial line field. If the field had an offset, you would be able to see wobbles in the magnetic field, which would give you the rotation rate. And the radio mission comes into this as well. So Voyager thought that was what they were seeing, was this rotation period. So this is part of the mystery, and this is work that's really been led by Leicester as well, Gabby Provan and Stan and Emma. And I'll start off here. So this is 10 days worth of data from Cassini, and this is the radio emission. These bursts are every 10.7-ish hours, and you can see this is the plasma data, the same as what we just saw, and then these are the three magnetic field components. You can see there's oscillations in all of these data sets, which are linked to sort of roughly around the rotation rate of the planet, but not exactly. So Voyager picked out these periods here, and everyone thought, great, that's the rotation rate. It's like Jupiter, you can pick it out through radio emission. And then Ulysses was a mission that was sort of observing the solar wind and went out as far as Jupiter and could pick this radio emission up. And they saw that the period had actually changed quite substantially, too much for the planet to have slowed down or sped up by. And then over the whole of Cassini, both the magnetic field and radio observations have given two periods, one for the northern hemisphere, which is in blue, and one for the southern period, southern hemisphere, which is in red. And these are varied across the whole of Saturn's years. So up here gives you an idea of how the sun is at the sun's latitude at Saturn. And so a Saturn year is around 30 years on Earth. And so Cassini was there for about half a year of Saturn year. You can see that these two periods cross around there. So what causes these, so this is a zoom in of some of the oscillations that we see in the magnetic field, and what causes these, and this comes on to then current systems 2 and 3, which I'll probably refer to as the PPO current systems or the planetary period oscillation current systems. Just to take away from this is that you have these current systems give you a magnetic field perturbation, which as these current systems then rotate around the planet, you then see those oscillations appearing in the magnetic field. And at certain times when you have an intense upward current, you see this burst of radio emission when it's in a certain sector of Saturn's magnetosphere. And so one key difference with these to the other current system that we saw was that these were thought to be oppositely directed on each side of the pole. So you have one pole that's on one side of the pole that's going in and out on the other side. And that's kind of key to how I then did some analysis further on. So I suppose the key questions for my PhD were, can we see the evidence of the modulation, this planetary period oscillation in the field line currents? And then if we can we actually separate them out, and then can we learn about their individual strengths and position? So to do that we used the 2008 data, which are these sort of sets of orbit here. This is looking down on the planet, so they came up really high latitude. And this is probably a more informative view where we look down on the northern pole here. These are the sort of statistical boundaries of the auroral oval, and this is where we cut through those field lines. And this is in the south. So the first sort of evidence is if we organise them by that rotational phase or rotational part of that magnetic field oscillation that we saw earlier. Let's just pay attention to the black trace here, which is an estimate of the current that's flowing in below those field lines. So if we start at the bottom here and work our way round, you can see that the black curve now is really flattened out. Then we come back round and the black curve has got this steeper gradient here, which is the upward field line current or the auroral current. And then as we come round to here, we get a really steep current now, which is that sort of, you can already see here, this is the two types that were picked out in that original study where you had a 1 sense of the change, and this has got 2 senses of change. So what we could do then, we did some statistical work where we binned up all of the orbits that were in these sort of phase sectors and then took averages, and then using that sort of opposite symmetry we're able to add and subtract them. So if you take, for example, this one and add them together, you will get something that looks like this and this one. So these ones should be roughly the same. They're at 180 degrees out of phase where you see the maximum currents, which are here. And if you subtract one of these from each other, then you remove essentially this signature and you're left with then the PPO current signature. So these are the overall profiles that we see. So in the south we had a nice picture where we had this independent or static system, which was that current system 1, and then this is current system 3. In effect it's the southern system, where you have just a sheet of current that's oppositely directed at 180 degrees apart, like those meridians, and it's in the book as well, the current system there. In the north though is a lot more tricky. So in the north we found that actually both of the PPO systems, so that northern system and southern system, were both controlling the field line currents and both modulating them. So actually it showed that there was closure from the southern hemisphere into the northern hemisphere. So if I go back a few. So here what I'm talking about is that this current here actually went all the way up and closed in the northern hemisphere. And likewise this one then came all the way down and closed like this, and then back through the magnetosphere, through the plasma. So it's first evidence that these loops were interhemispheric. It's the first direct evidence of that at Saturn. On to you go. So this is a little movie just to try and illustrate what I've been talking about, which is you have this green profile, which is the static one, which was current system 1, and then on top of that we have the red one, which is essentially current system 3, which is the southern PPO one. Then as this rotates around, so this is the rotation angle, so basically once you get to 0 and 360 it's the same and it resets. And at 90 we have, or at 270 we have this extension that gives you the this longer intense upward current, which gives you more intense aurora and radio emission. And then at 90 you see it pushes up and you actually have a reduction of that upward field line current, or a reduction in the aurora. And this has also been seen in the aurora and radio emission data. And also you can see this like sort of cam, or this sort of motion here will give you that oscillation that we saw in the magnetic field data. So this is built from doing so this is essentially just taking these profiles, this one and one of these, and then animating it to get that out. So I suppose this brings on to like, what does all of this mean? So we saw that Saturn's these auroral currents, or field line currents, were modulated by the phenomenon that's the PPO, or the planetary period oscillations, and they're modulated in terms of their form, so that's their structure, also their strength. So you saw that we have quite variable strength. You have almost a doubling of the current depending on the phase, and also the position. For the first time we were able to separate the static and the rotational current systems, so that's like separating out this one that's linked to just the large scale coupling between the planet and the magnetosphere, and then also these rotational ones to do with the planetary period oscillations. We saw in the south that there was just the static one and this one rotational southern system. I looked for the northern one, we couldn't find it, and that's another talk, I suppose, about the dominance between these two systems. But in the north that we saw that there was the static system and both planetary period oscillation systems. You see the northern system and you see the southern system, and that gives you the first direct evidence that there was this interhemispheric closure of field line current. So all of these results really have implications for the aurora and the radio emissions. So the aurora and the radio emissions are kind of driven by these upward field line currents and how they accelerate and change the plasma. So it accelerates plasma down into or electrons into the upper atmosphere, that gives you that auroral emission. And so now we also have a handle on the typical position and strengths, which has been key to the end of mission, which is what my current sort of role is looking at. So this is just to give a brief overview of Cassini's final sort of dying orbits. So the ones in green just cut through the outer edge of the rings, and the blue ones come through and cut just in between the planet and the rings. And so we, on all of these orbits, cross the region where we see these intense auroral current signatures, and they're a key problem for people that are interested in the internal field, so the field that comes from deep inside Saturn. When you start having these extra signatures that appear in the data close to when we're really close to the planet, they can distort the models that you have fit to the data. So I'll just end with a NASA video sort of summing up the Cassini mission and sort of saying thanks to it. I'd like to say thank you to Cassini for allowing the data collection to have a PhD, and there's probably plenty of people from Leicester that have got their PhDs through Cassini data. And I would also just like to say some personal thanks to my two excellent supervisors, Stan Cowley and Emma Bunce, to my office mates Gabby and Snow. Well, Snow's actually was a little puppy. Katie, Sam, Matt and Tim, so my office mates that I was at Leicester with. And also just everyone who's like past and present at RSPP, which is the plasma group, for being such an amazing group to do a PhD in. Yeah, it's a really cool place. And thanks. Any questions?
Fascinating talk. I'm sure you'll agree. Greg said he's got time for a few questions if anybody wants to ask any. But I want to start with a really silly question, maybe. So I'm from anaesthetics, so this is as far away as Saturn is really. What do we know about the weather on Saturn?
The weather.
And do your magnetic fields affect the weather?
So the weather, you have, I don't know if we've got any good pictures. Well, there's probably some in there. The weather, so you have these large storms. So there was in 2010, there was a large storm which appeared in the northern hemisphere, which was called the Great White Spot, which then over a period of about a year wrapped itself all the way round with like it heated the atmosphere a lot. Well, I can't remember off the top of my head. But you have like really strong winds, so you have sort of kilometre plus a second winds. I mean, huge winds that in these like zonal. You have these big zonal flows. So like Jupiter, you get the really fine belt structure. You also have that at Saturn, but it's less pronounced because the colours aren't as good. In terms of whether it affects the magnetic field, and that's a really interesting question actually. So there is one of the leading ideas for what drives current system 2 and 3. If I go all the way back, there is actually something. No, that's too far. So these red dashed lines here are theorized flows that you would have in the upper atmosphere, which act as like a dynamo to drive these field line currents. So it's very possible that you could have a weather system where it flows in the charged atmosphere, but it's still weather, I suppose, which could then lead to this driving of a current system that then goes into the magnetosphere. So if you had really abrupt changes to how the flows were happening in the magnetic field, in the ionosphere, in that upper atmosphere, charged atmosphere, you could then maybe see changes in the observed properties of these of the currents and their periods. And we do see evidence that the periods. So I saw that they show the periods vary with time. In particular, they seem to vary with Saturn's season and change with Saturn's season. So it's kind of implying that they're coming from the polar regions, which is why we have these theorized flows here, and then also why you get that seasonal variation. So as you light one hemisphere, you change the flows there, and that changes the current, and that changes the rotation that these currents rotate at. So that's a really interesting question, actually. Weather effects.
Questions from anybody else? Any other quick questions? Okay, we'll be downstairs for some wine at later on, so there might be an opportunity to ask some questions. Have you got can we just get a picture for the record?
Sure.
And then we can swap over. Shameless, this is this is shameless. Doctoral College. Congratulations. Nice one. Thanks. Thanks a lot. Thanks again.